Now we're going to continue our discussion of the solution of the problem. So for the given figure, a section of the beam is overhang. So we have to separate the overhang from the rest of the beam. So we are going to separate member 3. So if we're going to separate member 3, so this will be treated as statically determinate structures, and the rest of the beam, which is from member 1 to member 2, is statically indeterminate structures. So we're going to analyze the overhang beam as statically determinate structures. So for the overhang beam, so this was for the overhang beam. So this is our overhang beam. So which means that if there is on the cut section, which is a joint C, so we have here, there are forces that will be acting on the cut section. So we have here 20 kips. Of course, there will be a shear force which has also 20 kips, so that it will be in equilibrium. And there is a bending moment force which is equivalent to, so 20 kips times the distance towards point C is 10, so that makes 200 kips. So this will move in a counterclockwise direction, so it will have an equilibrium to our it will cause equilibrium in our beam. So we have now our moment bending force, which is 200 kips feet. So this 200 kips feet, of course, this will also act on the other side of the beam. So we have here 200 kips feet. So now we have done analyzing the overhang beam, which is statically determinate structures. We're going now to analyze our statically indeterminate beam. So if we're going to analyze this one, so which means that, so this is now a statically indeterminate beam. So if we're going to analyze based by this can be analyzed by stiffness method. In our in the requirement, what is being required in the problem is to identify our joint load vectors. So for this one, for our beam, so this is now statically indeterminate beam. So if we're going to identify, so there will be two joint load vectors. We have P sub 1 and P sub 2. So these two joint load vectors, P sub 1 and P sub 2, will be equivalent to the external load that is acting on our original beam. So if we're going to identify now our joint load vectors as we analyze our statically indeterminate structure, so which means that we have two joint load vectors. We have our joint load vectors P, which is equal to P sub 1 and P sub 2. So therefore, if we're going to identify now the value for our P sub 1 and P sub 2, we go back to our statically indeterminate structures. So that's member 1 and member 2. So there are forces that is acting, which is a bending moment force. We have here 50 kips and we have our 200 kips. So it will create a clockwise direction. So for this one, for clockwise, we use negative sign. So this will be equivalent to negative 50 and negative 200 kips. So these are both in kips feet. So those are the value for our P sub 1 and P sub 2. Now we move on to member stiffness relation. So for this one, for member stiffness relation, we're going to establish the relationship between our member end forces and member stiffness coefficient and member end displacement in the local coordinate system. So basically, this will be the equation. So our equation will be equivalent to Q is equal to K times U plus Q's of F. We have to take note that we have our Q's of F, which is to represent, actually Q's of F to represent the forces that would be developed at the member ends due to the external load if both ends of the member were fixed against translation and rotation. So for this one, we have our uh, formula now to have the value for our member end forces in the local coordinate system denoted by capital letter Q, and that is equivalent to K times U plus Q sub F. Of course, in our previous discussion, we are familiar with Q is equal to K times U. However, for the beams, we have here an additional to our formula, which is plus Q sub F, and we have to take note that Q sub F is a forces that would be developed at the member ends due to the external load that is acting if both ends of the member were fixed against translation and rotation. So the same concept with our previous discussion for plane truss. So there are for member end forces. For every member, there will be four member end forces in the local coordinate system. And of course, there will be also four member end displacement in the local coordinate system. And an additional, there will be four Q's of F in for every member of our beam. So which means that if there will be three members of the beam, so we have to identify, we have to determine Q sub 1, Q sub 2, and Q sub 3. And for every member, you're going to make use of this equation, wherein for every member, for example, you have Q sub 1 equal to, you have Q sub 1, Q sub 2, Q sub 3, Q sub 4 is equal to our K, which is our stiffness matrix in the local coordinate system represented by small letter k multiplied to our member end displacement in the local coordinate system plus our Q's of F. So we still have 4 Q's of F for every member. For our K, for our local stiffness matrix, this is the formula that you will be using. So you simply have to identify for every member, identify the value for EI all over L cube, then multiply that one to this elements in matrix form so that you could identify the stiffness matrix in the local coordinate system represented by small letter k. Now for this example, we're going to identify our member stiffness matrices for the members of the beam. So which means you have to identify your K sub 1 and K sub 2. So that we could identify your K sub 1 and K sub 2, we have to identify our EI all over L cube for member 1, then substitute that one to our equation. Then you also have to identify your EI all over L cube for member 2, then substitute to our equation. Now we move on to the determination of our member end forces due to the external load. So which means that from our equation, Q is equal to K times U plus Q sub F. So we have to identify now our member end forces, our member fixed end forces, Q's of F. So we have, for example, a member is being loaded by a concentrated load. So that concentrated load is denoted by W. So for example, that is denoted by W. So which means that you have to take note that for every member of the beam, you have to assume that it is fixed. So which means, for example, we have two members of the beam. So for every member, so that we could identify the value for our Q sub F, we assume that that is fixed. For example, we have here a beam. So we have here member 1, and you have here your member 2. So if you're going to have member 1 for your Q sub F, the value for Q sub F, we have to, if you're going to have that one, we're going to assume that member 1 and member 2, those are fixed. So we are going to assume that those are fixed. So as we assumed, we're going to have here our identified forces that will be acting. So if you're going to identify the forces that is acting, you have here shear force in a vertical direction at the beginning of the member. So F's, we have the moment force at the beginning of the member. Same also, we have also our shear force at the end of the member, and we have our moment force at the end of the member. So which means that to denote that it is shear force and moment force at the beginning or at the end of the member, so we're going to have here FSB and FMB. So that is shear forces and moment forces at the beginning of the member. Then for our at the end of the member, that is FSE and FME. So that is at the end of the member. So we have to take note that our shear force and moment force, this will be equivalent to for at the beginning of the member, that is the equivalent value. So you have here our equivalent value for our shear force at the beginning of the member, and this is our equivalent value at the beginning of the member for moment force. At the end of the member, this is the value for our shear force, and this is the value for our moment force at the end of the member. So we have to take note that this equations, these forces, of course, will be up this forces, the equation that is being illustrated is applicable only if the load that is acting on that particular member of the beam is a concentrated load. So which means if that is a concentrated load, you're going to make use of this. And for this one, if we're going to have now our equivalent values, so therefore in matrix form, if we're going to identify now the value for Q sub F, so that is equivalent to, as mentioned, there will be four member fixed end forces in the local coordinate system for every member. So you have here Q sub F sub 1, Q sub F sub 2, Q sub F sub 3, and Q sub F sub 4. And you have to take note that for Q sub F1 and Q sub F2, those are shear forces and moment forces at the beginning of the member. Then Q sub F3 and Q sub F4, those are shear forces and moment forces at the end of the member respectively. Then if we're going now to identify what will be our shear force, our moment force, we're going to write that the equations a while ago that was presented on the illustration on the figure. If we're going to write that in matrix form, you have now this one, Q sub F1, actually this one, this value for our shear forces and moment forces at the end and at the beginning of the member is equivalent to this equations. So we have now our equation for our member fixed end forces at the for every member of the beam. So you have here your equations. So these are now the equations for our fixed end forces for every member. So we're going to make use of this. We have to identify our capital W. Of course, as mentioned, capital W is the concentrated load that is acting on the member of the beam, because we're talking about per member. And of course, our I, that is the moment of inertia, our L is the length of the beam. Moment of inertia of the member, L is the capital letter L is the total length of the beam, and our L sub 1 and L sub 2. So we have here, sorry, it's not moment of inertia. Those are small letter I sub 1 and I sub 2. I sub 1, small letter I sub 1, and I sub 2 represents the length of our member. So you just have to identify the I sub 1, L sub 1, small letter L sub 1, and L sub 2, which are the length of the member as illustrated on the figure. So you have to identify that this is only applicable for concentrated load. However, for example, there is if the beam is subjected to a triangular loading, and you have here a uniform loading, so you cannot apply this equations. So what you're going to do is, for example, member 1, that is a triangular loading. You have member 2 for our uniform loading. You go back to TOS 2. So in TOS 2, you have equations on the shear forces and the moment forces. Now, if there is a combination, for example, for member 1, for example, this is member 1, you have concentrated load, you simply have to add the shear forces and moment forces. You simply have to identify for our triangular loading, concentrated load, and uniform loading. Of course, for concentrated load, these are the formulas that was presented a while ago. This one, triangular loading, refer to TOS2.